root data in AOD.root format, but in run 3 and onward, we will use AO2D.root. And the analysis framework is also different. In run 3 and onward, we will use the O2 framework instead of AliPhysics. And the main difference between this analysis framework is that in AliPhysics framework, we generally deal with the object, root object. When you do some analysis, when you call some track or event, those are in root object. But in O2, we will deal with another format that is called data table. That means we will store our information in some table in format of some columns, and from there we will access our information. So before starting the analysis framework, so here are some useful link that will probably help you in order to understand this O2 analysis framework. So for the starting point, you can look at this link where this documentation of O2 framework is written. I think it's written very well. One can look at it and can get some idea. And if you have any trouble with the O2 framework, so I will propose you to join this two Mattermost channel where we generally discuss the problem that we face when we using this O2 analysis framework. So this O2 framework one can install using the alibuild, and if you do not have the alibuild in your laptop, you can install it by just following the command in this link. Then in order to install the O2 framework, one can follow these comments. For example, you need to make a separate directory where you need to download the O2 and O2 physics by using this alibuild command. Then you can build your O2 and O2 physics by using alibuild build command. Then one can directly go to the O2 environment similar to the AliPhysics using this ali enter. So remember, when we enter the AliPhysics or aliDoctor session, we generally put this AliPhysics latest, but in order to get into the O2 physics environment, you need to put here the O2 physics. And before doing this installation, please check your prerequisites by this command. Now, so what are the basic steps for doing the analysis in the O2 or in the run 3? So the steps are following. So first, we need to add our analysis task in any existing directory of O2 physics. So under the O2 physics, you will find several directory representing several PWG like PWGCF, PWGLF, PWGHF, and so on. So under those directory, you will get a folder called tasks, and you need to put your analysis tasks there. Then you need to rebuild your O2 physics framework by using the same command that we used when we first built the O2 physics software. Then you need to test your code. For that, what we suggest, you should download some AO2D.root file. So now we are converting this run2 data in AO2D root file, and the information are stored in grid. So from there you can download some AO2D.root file, and then you can run your code locally over this AOTD.root file. If everything is fine, then you can make a pull request in the O2 physics Git repository. And once the tag is available, you can run in the Hyperloop. Please remember here that's for the O2 physics means in the run3 data, we are going to use the Hyperloop instead of train. So in the end of my presentation, I will come to this Hyperloop, how to submit job in Hyperloop and so on. And if you are not experienced with using this Git repository, how to work with the Git repository, you can always follow this Git tutorial where every step is uh, main, uh, written very well, and you can get information how to how to make the pull request and also on. Now let's first start with the AO2D data. How can we download this AO2D data? So in your Lego train, if you go to the train called run 3 conversion, where we are generally now doing this conversion from run 2 data to run 3 data in order to make a analysis framework and validate it. So there you can find several, if you go at the bottom of this run if you go in this train run 3 conversation, and if you scroll down and go below, you will find the several job number that I have shown here. You can see here there are several numbers. So these jobs are basically for the conversion from AOD data to AO2D data. And if you click any of these job, for example, here I have just click this 233, which is corresponds to a conversion of LST20F6, you will get this window. And then if you click on the test result, you will get the various step of the conversion, which is mentioned here. But you, in order to download the AO2D file, you need to go at the end of the page, and here you will find full train and the option of output. And if you go to the output, you from there you can download few files of this AO2D converted AO2D.root data. Now you can use this AO2D.root data in order to validate your own task. Then you can make a pull request of your task, and you can do analysis in the Hyperloop. Now let's come to the analysis framework. So here, here I put a structure, a basic structure of writing a task in this O2 analysis framework. So just remember that these upper lines are compulsory for every analysis task. This is basically a license, and here you can describe your code, your task, what it will do, and how it will work. So those description you can put here. So the main task have mainly have two bodies. One is the struct or the structure function. Another is the data processing function. So in the structure function, you will in this structure function, we will basically we will write our analysis task. Means we will put our event loop, track loop, all the analysis step, and then you need to use this define data processing. So this structure task, it can be added to any kind of workflow via this adaptAnalysisTask helper, which is shown here. So what you need to do, you just need to put the name of your task, which is basically my task, for example, here, and you need to give a name of your task. So when you will do the building, or if you when you complete your whole analysis task, then you need to do the rebuild. And when you will do the rebuild, you will get a execute macro corresponding to your analysis task, which and you will run this execute macro to validate your task. And the execute macro will have the name that you will give in this bracket. Now let's go to more further. So first, in order to write analysis task in O2 framework, we need to put two default in header, that is the analysis task.h and run data processing.h. And in addition to that, you can also put some default namespace. Now, as I mentioned earlier, that whole our analysis will be done inside this structure my task. Now let's see how one can do some basic analysis. So in order to run your analysis over some event or track, you need this process function. So you can see inside this process function, in this bucket, we have two objects. That is, one is the collision, another is the tracks. And what is this collision and tracks? So this collision and tracks are basically a data table where we stored our information of the collision and the information of the tracks. I will come to it later. Then you just you just give a name of the tracks here, and you can use the track loop like this way. So basically, you doing this, what you will do, you will basically access your all the available event in your AOD.root, and for each of the event you will run a track loop, and the track loop you can run it by using this format. Now, as I mentioned that this AO2D, this O square AOD collision and this O square AOD tracks, those are basically the table. And this table is made by reading the AO2D dot root data. So basically we read this AO2D dot root data and store this information in some columns of a table. Now, in O square framework, we basically have three types of table. One is default AO2D table, one is helper task table, another is derived table. So what is this AO2D default AO2D table? So this default AO2D, in default AO2D table, we basically contain the base information of from the basic information from the data, such as track information, momentum, or the collision information, collision vertex, and so on. Now, we also have another table that is called the helper task table. So this helper task table is the additional table that we also used in our analysis. And in this helper task table, we basically stored some we store information regarding PID or the V0 or cascade track and so on. Now there is another table that is called the derived table. So this derived table we make from our own task. For example, in some complicated analysis such as heavy flavor correlation, where we correlate to heavy flavor hadron, in that case, we will generally use this derived table. So what we do, we generally split our analysis task in complicated analysis in two steps. In first step, we store some, for example, let's say for case of heavy flavor correlation or the correlation between D0 and D0 bar, first we select the D0 candidate or the heavy flavor. Hello, is there any question?
Hello, please mute all the participants. Please mute yourself. Anyone has any question? If not, please mute.
Okay, so as I mentioning
Chalo.
that this derived table is formed from our own task. For example, complicated analysis like heavy flavor correlation. So we do those kind of analysis in two steps. In first step, we select our heavy flavor candidate from the available track and collision table. Then we use those heavy flavor candidate to make some correlation. Now this heavy flavor candidate, one can store it in some data table, and this kind of data table is known as the derived table. So we'll store the heavy flavor candidate in some derived table. Then when we do the correlation in next analysis task, we'll use this derived data table of which contains the information of heavy flavor candidate, and we will do the correlation. So in today's presentation, I will mainly talk about this AO2D table and the helper task table. I will not go to the more complicated one, that is the derived table, but you can always go to this link of this O-square analysis framework documentation, and there you can find some example how to write this derived table and how to store data there. Now let's look. Now let's have a look of this AO2D table. So in O-square framework, we have several AO2D table. So I have listed few of them in left hand side. You can see the table which name is BCS, that is basically the table corresponding the branch crossing. Then collision, which basically store the information of collision. Then track. For the track, we can see there are various kind of track like tracks, track covariance. Then we will also have the track extra. So these tracks are basically stored the different kind of information. Basically the track store very basic information like momentum. But if you look at that table for track extra, that will contains the information of the detector. When you reconstruct the track using the detector, it will, you need some detector information. So those information are basically stored in the track extra. For example, number of cluster of TPC, a number of findable cluster, and so on. So as I showed in the previous, in my the first example, In first example, we used this table of for the table of collision and the table of tasks, table of tracks. So let's first look what this table of collision contain. So here in the right hand side, you can see here I have shown the basic description of the table named collision and what it contains. So you can see it contains a various object like branch crossing ID, position of vertex X, position of vertex Y, position of vertex Z, as well as the covariance of X, covariance of Y. So this covariance is basically used to calculate the vertex resolution. When we reconstruct the vertex, it also have some resolution of reconstruction. So those resolution is calculated using this covariant and so on. And in order to extract this information, for example, if you want to extract the information of Z vertex position, you need to call this position Z, pos Z. So, and you can see here in the right hand side is the what are the this variable corresponds, that is basically mentioned in the right hand side. So you can also go in the OSCAR and physics framework documentation, and there you can look at any of the table that you want, and you can see there which variable it contains and how can you extract the variable in your analysis task. Now let's go to the track information or the track table. So you can see that in the track table, we have several information like phi, px, py, pz, sign of the track, pt, momentum, eta, its collision ID, which kind of track it is, it's a global track or short track or standalone track. All those information is basically stored in this tracks table. Now, as I shown that we first what we did, we make a structure of our analysis task. Then we put a process function in order to access the event and track. Now what you need to do, you need to store the information of your analysis, and you can store it in some histogram. And in order to book histogram, the O-square framework also give us some special kind of class that known as the histogram registry. And using histogram registry, you can perform several type of histogram uh, several type of histogram analysis. Means you can add something, divide something, scale something, those kind of thing you can do using the histogram registry. And you can also define your histogram inside of the histogram registry. For example, at the beginning of my task, you can see this is my structure of my task, and here is the process function where I extract the event and track information. And just above the process function, you can also define your histogram that you want to fill. In order to do so, you need to first call a array or the vector of the registry that called histogram registry that I named here the registry. Then inside the registry you can put any kind of histogram. For example, here I have put two one-dimensional histogram and two three-dimensional histogram. And in this histogram, the first name is corresponds to the histogram name. The second name is basically the histogram title, and in the bracket you need to define the type of the histogram as well as the condition of the axis. Means, for example, if you look at this three-dimensional histogram, the first uh, quantities in this first curly bracket corresponds to the number of bean and the range of axis for the first axis, and this is for the second axis, and this is for the third axis. So in that way one can initialize the histogram. Then what we need to do, we need to fill this histogram inside the track loop in order to get some basic track information. Now let's say how we can do it. So here I put some example, you can see here. So the first example is that I filled the histogram, that is the age VZ. I fill the vertex Z information. So how can you fill it? You just need to call the registry.fill. Then you need to put the name of the histogram, what you want to fill. That is basically here is the age VZ. And then you need to put the quantity that you want to fill. So here I fill this collision.p pos jet. So this collision is basically the collision table. And as I mentioned in my earlier slide, that by calling this pos jet, you can extract the information of vertex jet. So we just call this and fill the information of vertex jet. Similarly, in these two histogram PT and histogram PT eta phi, I fill the information of the PT from the track table. So you can call the track.pt and the track.pt, track.eta and track.phi in order to get the pt eta phi information of the track. Now, this is a very simple task to fill some basic variable like pt, eta, phi, and so on. Now, as I mentioned that this track table contains very basic information like px, py, pz, eta, and so on. But if you want to fill some additional information like information from some detector like TPC cluster or TPC findable cluster, so those information is not stored in this track table, but you can always join this track table with the table which contains those information. And before going that, just let me show you that. So here we have defined all the tasks. Now let me just show you how one can compile and check if the task is working or not. So in order to do so, you need to follow the following step. For example, this you can put this task under this pwglf task folder. Then you need to modify your C. In that folder, you will also get a folder that calls you will get a file that called the CMake list. So this file is basically used when it's building, when it's do the rebuilding. So here you can see there are several blocks, and you need to add a similar kind of block for also for your analysis. For example, here you can see here I have added a block for this my task, where I put the name of the task. This is the Alice India School my task. So from where I get the name, so if you go to the previous slide, you can see that in this data processing, we have defined the name of our task like Alice India School my text. So you need to put that name here. Then you need to put the source file, that is the mytask.cxx. Then you need to put the required libraries that your analysis task needs. After doing that, you need to rebuild using this alibuild. Then you will get a execution function which have a name O square analysis LF, then the name of your task that you give in this data processing or in the CMake list here. So this first thing, so this O square analysis is common for all the tasks. And the second and the third term, that is LF, it depends in which working directory you put your task. So as I put my task in the pwglf, that is why here when I get a executable file, I will get this LF here. If you put it in the pwgf then you will get a HF here. So you need to run this execution task in order to validate your code. And how can we run it? We can run it by just using this command. So what is this command? So first is your name of your executable task, that is the O square analysis LF Alice India School my task. Then you need to add this command //AOD, sorry, dash AOD dash file, that will basically give you to access to run over some AOD file. Then you can put the name of your AOD file. Then you need to put -b. So this -b corresponding to run in a batch mode. So if you run this command, you will get some output that will have a name analysis result.root. And if you go into the output, you can first see a folder, and the folder will have a name same as your task, and inside the folder you will have the histogram that you filled. For example, here we fill the VZ, PT, and the three-dimensional PT eta file, and you can see here is the distribution of the PT. Now, as I mentioned earlier, that these tracks, all the track table only contains a very basic information. In order to extract more information, you need to add this track table with the other table. For example, here you can see here I have add this track table with another table that called the tracks extra. And how can we add it? We can use the join command, that the SOA then double colon then join, and inside the this bracket you can put how many table that you want to join. You can want to join 5 or 6 different kind of table of track. You can put it here. It will basically merge all the table and it will get the information from all the table. Then one can extract the information of, for example, TPC number of findable number of findable cluster from the TPC by just calling the TPC NCLS findable, by calling the track.tpc and CLS findable, and one can fill it in the histogram. So one need to remember that this TPC and CLS findable, this variable is not present in this tracks table. It present in the track extra, but if you join it, you can directly extract it. Now you can also run this simple code by using the similar command that I have shown earlier. Just you need to put the name of your executable task, then the name of your AOD file, then a -b to run it in the batch mode. Now, in my earlier slide, I mentioned that in addition of this default AO2D table, we also have some helper task table like PID table. So this helper task table is basically store some additional information which we need during our analysis, for example, PID. So in this example, I will show how one can use this additional helper task table and how one can extract some PID information. In order to do that, first one need to put the header file corresponding to that helper task table. So here, as well as I am going to use the PID table, and the corresponding header file is the PID response. Therefore, here I have put the header file of PID response. Then in the similar way, as the previous example, I just add another table, another helper table which contains the information of the PID, and the table name as the PID TPC full pion. So it basically contains the information of n sigma pion, and we can join it with the tracks and track.txt in a similar manner using the join. Then one can directly call the TPC n sigma pi from the track to get the PID information from the tag, and one can fill it. But remember, if you are using this helper task table, that means you are using some additional analysis task in addition to your own analysis task. Therefore, where you are going to execute it, you first, as similar to the previous example, you just need to put your executable name of your executable task, then the AOD file name, then the -b. Then you also need to put the task which corresponds to this additional helper task table. And that task is basically the O square analysis PID TPC full. Then if you execute this command, your code will be run and you will get the output file where this n sigma information of pion is stored. So always remember, when you are using the helper task, you also need to add the executable file for the helper task. In this case, it is O square analysis PID TPC full. So there are several helper task table, like you have the helper task table for the track selection. So for that, you need to join the track selection table here. And when you want to execute, you need to put the corresponding task of track selection after your own analysis task executable file. Now, we also have an option of configurable. So what is this configurable? So this configurable is basically, it gives us option to put some argument in our analysis task. For example, in run to data, when we did some analysis, we always put some argument in the add task, which we basically used when we run the train. So those kind of argument, you can put it here by using the configurable. So here I show an example. So here I put a cut on the track, that is the eta cut. So one can define this eta cut with this configurable. So for that, you need to call this configurable. Then you need to put the type of the cut, if it is a float, if it is a double, or if it is an integer or so on. You need to put the type, then you need to define the cut, that is the eta cut. You need to put a name here, then you need to initialize the value, then you can just describe what is this cut here. Then you can call this eta cut. Means here you can see, here I have just put the condition that the absolute track dot eta greater than eta cut, and then it will consider all the track, otherwise it will not consider. So what this configurable will do, so when you will after using this configurable, if you build your analysis task, it will give you option to put some additional argument inside your task. For example, if you want to execute this macro, you just put the name of your executable task, then the root file name. Then you can see here I have add another part. Here I have put the minus dash dash, then the name of the configurable. So what is the name of the configurable? The name of the configurable is defined in this colon, so eta cut. So you can put eta cut, then put 0.8, then put minus b and the additional helper task. So in that way, what it will do, it will directly take the value of the eta cut from your execution command, and it will use inside the code. In a similar way, you can add how many cut you want to use. You can add some pt cut, some cluster cut, some cut, and whenever you want to execute it, you need to put the initial value of those cut here in this executable in the during the execution command. Now there is also a way to put some means here you can see this cart or this configurable is just a single variable, but there is also a way to use a array of a cut. Means if you want to use some pt dependent cut, for some pt you want to use some cut, for another pt you want to use another cut. So you also means configurable is also allowed you to construct a matrix or a vector of this or a two-dimensional vector of this cut. And you can look so in this analysis framework documentation, there are some example you can look at there to see how one can call this two-dimensional cut. Means if you want to or some variable cut, one can look at there. Now with this so these are basically a simple and very simple structure to do this analysis in O2 framework. And and I think it will be a very good starting point to do the O2 analysis with some very simple analysis tasks. Then one can always improve it according to their analysis. So for that, you can always look at the documentation, and there you can find how one can write a derived table, how one can extract the information from there. So those scope of improvement is there. So you can also look at it. So I will not go to those advanced thing, but before ending my presentation, let me just talk something about this hyperloop. So in the run 3 and in the future, we will run our analysis task or our analysis in the hyperloop. It is means not possible. Means as you know that in run 3 we are going to take a huge amount of data, and just running those data locally means in your grid account, it's very much difficult to run those huge amount of data. Therefore one need to always means run the your analysis in the hyperloop. So this hyperloop is similarly to train. So in train, you know that we have some dependency wagon like centrality or some selection or PID response. So those helper task wagon is also here in the hyperloop. So in hyperloop, you will basically have two type of wagon. One is this helper wagon, another is the analysis wagon. So in helper wagon, you can see there are several helper tasks like PID top, beta, event selection, track selection. So these are basically the dependencies that we are going to use with our analysis task. So I will show how this dependency works. Now let's go to the main portion of the hyperloop that basically contains the our analysis task. So it contains the analysis task in some particular analysis list. So for example, here in the Hyperloop, we have an analysis list that names heavy flavor O square development for Alice 3, A open heavy flavor 2 point Tesla forward or so. Just forget the name. In this particular list, here you can find two things. One, in the left hand side, you can find the wagon name of your task, and here you can find some data set. Means in train, what we generally do, we assign some analysis task. Means when we run some train, we activate some particular run period or so on. So these basically are those particular run period, and one can do it directly from here. For example, if you want to activate, you want to run this HF task D0 over this LSC21D in LED, you just need to click here. And these are basically the task of your analysis task. So what this analysis task contains, so if you click on this HF task D0, you can see there are several things. The first thing is the name of your analysis. So whatever name you will give here, it will comes in this wagon list. Then you need to put the executable file of your task. So when you rebuild your analysis task in the OSquare framework and submit it in the Git by making a pull request, and when it is merged with the latest version of OSquare physics, this executable task will always be available in the Hyperloop. You need to click in this array, and there you can see your executable task if it is merged in the latest version of the O square physics. Then you just need to call the executable task here, that is basically the workflow name. And here you need to give the dependencies corresponding to your task. For example, for this task, I have only the one dependency, that is basically the HF candidate selector D0. So it basically, this task is basically select the D0 candidate and store it in some table. So this is basically the helper task for this HF task analysis. So I just put it the dependencies here. For example, in our previous example that I have shown here for the PID, you need to put the corresponding PID dependency here. Now here you can see there is another thing, the configuration. So this configuration is basically contains the argument of your task. So as I shown earlier, that one can put different kind of cart using this configurable, and I used this cart itamax cart. So those configurable or those argument will be automatically coming in this configurable of this hyperloop. So the name that you give here, for example, there in that example, I gave the name itacart. So if my task is available in the latest O square physics version, the itacart name will come here. Then I can manually change the itacart, whatever cart I want, and save it. And then I can just start my run by enable any of this data set. So if you enable this data set, first it will test, it will give you some output. And if there is no issue in the test, the train will be automatically submitted. For the moment, we now in the Hyperloop, we now generally submitted 310 in a day. So if you have some executable macro for running, you can just set your wagon and start your analysis task running on the Hyperloop.